Good evening, everybody. Today, we are going to cover the rest of the parts of the week 8. So, it includes the projection using inner product and Gram-Schmidt method is there and rotation matrices. Okay, so let's see some of the basics and then we will continue to the questions. So, how do we do the projection using inner products? So, to find the projection of any vector. So what do we do? Suppose I have two vectors and I want to represent, this is my first vector B vector, and I want its projection on this vector A. So basically I want to drop a perpendicular from here in case of dot product, I am saying. Okay. Basically we find out the projection in case of dot product most of the times. So this is the part that is lying in the direction of A. So this part we call as projection of B on A. So this is the projection. So how can we find it out? So you can see it is a triangle. So by the property, I can say that if this angle is theta and I know the magnitude or the length of this vector. So I can say that length of this vector times cos theta will be my this V vector here. Okay. So what I can say that this, how can I find this B? So I can get this B, or sorry, this is the length of this vector only. So I am not getting this whole vector. It is only the length of this vector I am getting. So I have to multiply it in this direction or a unit vector in this direction. So I can say that A vector divided by magnitude of A. So this I need to find out. Okay. So there are various ways of doing this. So one easier way, or I can rewrite this equation in this form because I know that A vector dot B vector is nothing but length of A times length of B cos theta, right? So I can write this B cos theta as A dot B divided by length of A. So in easier way, I can write this B cos theta as A dot B divided by magnitude of A. Already one magnitude of A is there, so square times, and here A vector I am having. This is some real number that I will get. Okay. So what I can say this length I can rewrite this part as well. So A dot B divided by A dot A I can say. Okay, both side I am doing the dot product and then A vector times. So this will be my projection of B on A. Okay, it is using the dot product, and if we are having inner product, so you can directly say that it will be A and B's inner product divided by A and A's inner product, and here A vector. This will be projection using the inner product. Okay. So how do we find out the projection of a vector on a subspace if subspace is given? So firstly, we will find out its basis. So whatever be the basis, and a basis has many vectors. Okay, it can have many vectors. So suppose my basis is there, and I have some vectors inside it, b1, b2, and b3. Let's say three vectors are there. Okay, in the basis. So what I can say that if I want my projection of this vector, some vector c, suppose c vector, I want my projection on this subspace that is spanned by this basis. So what I can say that c vector's projection on b1, okay, and c vector's projection on b2, and c vector's projection on b3, and then I will add them. One thing we need to keep in mind that this basis is not simply the same basis, it should be orthonormal. Okay, so this will be my projection in that case. If I want to project my vector on a vector space or a subspace. Okay, so for here you can see one example. So we are given a line y is equal to x. So you know that what will be the solution. So it is saying that all the points of R2 or all the vectors in R2 So vectors in R2 will be like this, x comma y, where x and y both belongs to real number. So this type of vectors, it is going to cover all for all x. Okay. And here y is equal to x already given. So I can say that all vectors in this form will be inside my this subspace. So you can see we can clearly find out a basis for this. So I can say that 1 comma 1. You can also use orthogonal basis here. Okay. Instead of orthonormal, you can also use orthogonal. It will also work. So here you can see this vector is spanning this subspace. So what I can say that about this vector is I want a projection of 1 comma 2 on this vector. So simply I can use the formula that is given above here, this one or this one, because dot product is used in this, no inner product is defined. So we will use the standard dot product here. So I can say that 1 cross 1 comma 2 dot product with 1 comma 1 divided by 1 comma 1 dot product with 1 comma 1, okay, times 1 comma. Here it is. So you can see that their dot product will be 1 plus 2 divided by, and their dot product will be 2. Okay, it will be 1 cross 1. So it will come 3 by 2, 3 by 2. So this will be my projection. Okay. In this case, we have two vectors inside our basis. So firstly, we see that these are orthogonal. So we converted this basis to orthonormal. Okay. And even if we didn't do this, still we can get our same answer. But it is standard way if you want to convert it. So it is okay to convert this vector to this basis into an orthonormal basis. So now it is orthonormal because you can see that both vectors are orthogonal to one another with respect to the dot product, and their norm is 1 as well. Okay. So now if I want to find out the projection of 2, 1, 3 on this vector, so the same way I will use, I will firstly do the dot product of this with this, and then I will multiply this. Here, if you have an orthonormal basis, in orthogonal, you have to write this. Okay. You have to use this formula or this one. Okay. But if you are having an orthonormal basis, so you know that this bellow part or this one, the length of A, it is 1 already. So you can directly say that A dot B times A vector. Okay. If it is already an orthonormal basis. So simply here you can see that it is already orthonormal here. So direct doing the inner product between these two vectors and then multiplying it by A vector means A dot B times A vector we are doing here. So this is the projection of this point B or this vector B on this beta 1 basis, this basis first vector. Okay. And here it is the projection of B on this basis second vector. Okay. So we got two vectors. Now if we add them, so I will get my resultant vector. Okay. Next is projection as a linear transformation. So projection, we have a transformation given here. That is nothing but transformation of all the vectors is equal to, it is given here that we will apply the projection and we will use this. So suppose you are having a 3-dimensional space and you want a projection. So this W is a subspace. Okay, suppose this is this XY plane, this plane it is. Okay. And you want your all vectors projection on this plane. Okay, so how can you find out? You can simply find out an orthonormal basis for this, and you can use its projection on these vectors of this orthonormal basis, and then you can add them. So it is saying that verify that T is a linear transformation. Yeah, it is a linear transformation because from one vector space, we are going to the another vector space. Okay, by some linear combination. So it is allowed. Next is what is the range of T? You know that every vector here will go in this vectors in this subspace. So its range will include, or its range will be equal to the subspace. Next, what is the rank? Rank will be same as the dimension of this subspace. If we are using a 2-dimensional to project, so it will be 2. And if we are using 1-dimensional, suppose only x-axis I am using for my projection, and rest 2 axes are still same. So I can say that the projection of my any vector on this one, it will go. So its rank will be 1 in that case. Okay. It will depend upon the dimension of W. Okay, same range and rank. Next is kernel of T. Kernel of T includes all those vectors that are perpendicular to the subspace or the codomain space. Okay, so suppose my vector, I have this plane and in 3 dimensions. So I have all the vectors that are perpendicular or in this direction from the origin. So this line is representing all the vectors that will be inside my kernel. Okay. Its next question is that, what will be the transformation of any vector v that is already on W? If it is already on W and I want to find out its projection, so it will be the same vector because its shadow on this subspace will be same. So it will be this. Here, one another thing is given that consider an inner product. We are given one inner product and we have to find out now the projection. Okay. Earlier we have used the dot product, but now here we are given some other function to be used as inner product. So simple, we don't have to do anything else. Just write down the formula. Here it is. That states that a dot b, not a dot b. Here we will use this inner product. Okay. And below it, we will also use a is inner product with a. And the value that I will get, I will multiply it in the a direction or a vector. So simple, I wrote this 1, 2 and 3, 4. I want the projection of this x in this direction 3, 4. So simply I wrote it and I did the inner product using this function a1, b1. So 1 and 3, 3 and 1 multiplied. Then minus a1, b2. So a1 and it is using it as a. This is a and this is b. So this will be my A1, this will be my A2, and this will be my B1, and this will be my B2. Okay. Basically, it is not going to make any change. Just when we are doing in our product, so you know that A cross B will be same as B. This is same. Okay. You can take anyone else other, but keep in mind that the vector that you are going to multiply after it, it should be in the projection space. So this 3, 4 we have to find out in this direction. So we will use it here as well as here. So same formula we used here and we got our answer like this. Any problem anybody is having? Till now, any confusion?
No, sir.
After this, we are given some another vector here 1, 2, 3 and we have to find out its projection on this basis. You can see that it is already orthonormal, right? So I can directly say that its projection will be 1, 2, 3 dot product with 1, 0, 0 times
100.
1, 0, 0, 1, 0. So this dot product will be nothing, 1, okay, and multiplied by 1, 0, 0, okay. And next I will find out its projection on this vector. So it will be
That will be
nothing
2.
but 0, 2, 0, okay. If I add these two, I will get this one, okay. Next is this. So next question in this one, it is saying that two subspaces are there, W1 and W2. And we have a vector space V and PW1 represent the projection of this subspace, this vector space on this W1. Suppose you are having a 3-dimensional structure, okay, here. And you have some vectors, okay, any vector you can have. Suppose here you are having a vector. This is your first projection, or I can say that this is your W1, this line, and this line is your W2. If you find out its projection, so it will lie somewhere here. And if you find out its projection along this, so it will lie somewhere here, this vector. Okay. So it is saying that projection of W1 plus projection of W2 is the projection from V to W1 plus W2. Okay. Then projection on of W1 on W2 and W2 on W1 will be 0. Okay, listen. What is it saying? That projection of, suppose I want this projection on the subspace. If I add these two vectors, all the vectors inside this W1 and W2, so it will be this plane. Okay, so this plane it is. So if I want its projection on this plane, so I said that we require two bases. two orthonormal bases or orthogonal bases. So if I have one basis here and one vector here and one vector here, so these are perpendicular already. So they are orthogonal bases. And if I use this, its projection over here, so it will be its projection along this direction and its projection along this direction. So if I find out its projection on these two vectors and add this, so it will be somewhere here. So this is giving me the projection exactly. So it is saying that it is saying that projection of W1 on W2, what will that be? So these two are perpendicular. So if I find out projection of one on another, so it will be 0. And same here, if I find out projection on one another, so it will be 0. It is equal to 0. I think this is correct, right?
Sir, W1 and W2 both subspace are different subspaces,
Yeah.
but what is the relation between them is not given. Then how come we have taken that they have to be orthogonal?
Okay. So if they are not even orthogonal, suppose they are not orthogonal. Okay. Suppose they are not orthogonal. One is this one and another is this one. Okay. So now you can see that if I add these two subspaces or if I find out all the linear combination of these subspaces, so it will lie along this whole plane, right? It will lie on this whole plane. And I can find out now some orthogonal basis because I want to find out the projection. So I can derive any orthogonal basis for it. I can find out by myself. Even if it is not given, I can still find out. I'm not saying I will use exactly the same one that are the basis for W1 and W2. After adding these two subspaces, the resultant subspace that I got, I can find its, what do we say? I can find out it and basis for this one, this subspace, whole subspace. I have
Sir,
W1. Yeah.
can you take two vectors and can you show
Oh,
that? It would be helpful actually.
suppose you have a vector 3, 4, 5, and you want to find out its projection on this X, Y. Sorry, you have two subspaces. First one is this, where you have uh, y x comma 0 comma 0, right? And second one is your uh,
Sir, for simplification, just take two dimension only, sir. That will be easy.
okay, dimension you want. In 2 dimension, it will again cause a confusion here. In 3 dimension, it will be easy.
Okay, fine. So then to proceed the
Suppose
way
you
you
have a
want.
yeah 3, 4, 5 you are having. So I have my subspace W1. That is all the vectors in this direction. I can say that span of set containing 1, 0, 0. Okay. W2 I have span of all the vectors using this 1, 1, 0.
Sir, why are we specifically taking like I'm just asking because in this one we are taking only a 1D vector, one dimensional vector, right? In W1,
Yeah, yeah,
0, 0, and in W2 we are taking only a two
yeah.
dimensional vector. So like any specific reason we are taking, or we can take three dimension
No, no,
also.
no. You can take any
Okay,
dimensional vector.
okay. Please carry on.
To avoid other certain cases, I am just taking this to be more means more concept can be defined from this. So that's why I'm taking one dimension. I'm
Okay.
taking two separate spaces here. So I have these two. So now if I find out if I add these two subspaces W1 plus W2, so it will include all these vectors and their vectors. So span if I have, so I can form all the vectors in R2 or not R2, all the vectors in this form x comma y 0. So now I can get a orthonormal basis for this. So what will be my orthonormal? I will take some standard 1, 0, 0 and 0, 1, 0.
Yeah.
Okay, I'm taking some standard basis here. And now these two are orthonormal. So I can clearly find out its projection on this one. That will be 3, 0, 0. And its projection on this one. So it will be 3, 4, sorry, 0, 4, 0. And if I add these two, so this will be 3, 4, 0. Okay. So it will be the way of finding projection. It is saying that suppose I have a vector, sorry, if I find out projection on W1, any vector I am having, this 3, 4, 5, if I find out its projection on this one, 3, 4, 0, and I apply the projection of this 3, 4, 0 on this W2, projection of V to W1. Okay. So if I find out this, the projection of this 300 on this subspace, uh, the projection of W2, sorry, this one, this projection on this vector. So it will be nothing but zero vector because both are lying in orthogonal directions.
Okay.
Sir,
Yeah,
for the projection of 345 on 110, the
yeah,
subspace, shouldn't it be the inner product of those divided by the norm
yeah,
of
yeah. That same thing
so,
I do. Inner product is not given, so I am using standard dot product here as an example.
so when you take inner product, it's coming out to be 770.
Sorry. 7,
3
7.
into 1 plus 4 into 1, that gives 7.
So your W2 you are finding out here, right?
Yes, sir. Yes, sir.
No, I am not using this basis. I require orthogonal basis, right? To
Okay, so
find
you are
the
okay.
projection.
Okay, okay,
We are
fine, fine.
using
You
this
have
basis.
already converted. Got it.
Yeah. That's why I converted it. Okay, so
Okay.
its projection on this is 0, and the projection of this on this also 0. So that's why it is 0. Next, in this one, it is saying that projection of W1 on W2 will be equal to projection square. Is not a projection from V to W1. Okay, if I find out projection of any vector, suppose 3, 4, 5, I am finding on this vector. So it will be 3, 0, 0. And if I again apply its projection on this vector, so it will again be 3, 0, 0, right? So it is saying that it will be the projection square is not a projection. It is saying that it is not a projection, but it is actually a projection of this vector on this one because this vector is matching with this. Clearly, if I want to say this, I have a vector 3, 4, 5, and I find out its projection on W1. So I got 3, 0, 0. Okay. So it is a projection from V to W1, right? Now I find out W1, this vector's projection on W1 again. So what will be it? It will be again 3, 0, 0. So now it is saying that it is not a projection, but it is a projection. We have seen that 3, 4, 5, if I match it with 3, 0, 0, so it is a projection from V to W1. So after 3, 4, 5, I apply projection here, again applied the projection. So whatever I got, it is again a projection. So that's why the statement is wrong. Next is, a matrix representation of PWT is given, then A cannot be a symmetric matrix. Okay. It can be a symmetric matrix. Suppose I have a matrix like this, 0, 1, 0, 0, 0. We know that the projection matrix, if we are using, suppose I am giving this any matrix I am taking here. So this can be my projection matrix, right?
No change.
No change. So it is symmetric. It is possible. Means every vector I am using,
It's
no
mapped
change.
to
I am
itself.
representing it on itself. Yeah. So that's why it is also wrong. Fourth statement is there. Projection of W1 minus projection of W2 is a projection from this to this one. So if I have a vector here, and suppose these W1 and W2 both are same. In this case, it is not given, they are distinct. Okay, suppose these both are same. So if I find out its projection on 100, so what will be that? 300, right? And if I subtract projection on W2, so it is the same W1 and W2 both are this span of this vector. So what I can say that its projection on this one will be 300, right? And if I subtract it, so I will get a zero vector. Okay, I am getting a zero vector here. And if it is a zero vector, so it is not a projection of this vector on W1 plus W2.
Sir, can you just repeat that once more?
Okay, one more time. Just take, okay, if it is not possible, then let's do this. It is not okay. So what you can do, suppose this is your W1 that is spanned by this vector, and W2 spanned by 0, 1, 0. Okay, distinct you can take. Okay, so if I find out projection of this vector on this, so it will be 3, 0, 0. And if I find projection of this vector on W2, so it will be 0, 4, 0, right?
Yes, sir.
So if I subtract it, so 0, 4, 0. So it will be 3 minus 4 or 0. And we know that the projection of this vector on W1 plus W2, what was that? It was 3, 4, 0. But here we are getting 3 minus 4, 0.
Yes, sir, got it.
That's why it is wrong. It should be plus here. Okay. Next is orthogonal basis is given here. This one.
Sir, sorry, please don't mind. Sir, what did you do in this one? PW1 plus PW2, you said it's a correction here. Can you come again? Yeah.
Here what I said that projection of a vector, any vector I am taking. So 3, 4, 5 I took. I find out its projection on W1. So
Correct.
W1 by this one. Okay. So its projection was this.
Correct.
Okay. Projection of this same vector on W2. So W2 was my spanned by this vector. So I find out its projection is this.
Correct.
If I subtract it from this, so I got this vector. So it
Correct.
is saying that it is the projection, it will be equal to the projection of V on W1 plus W2. But here we found that if I find out a projection of 3, 4, 5 on this W1 plus W2, so it was 3, 4, 0.
Correct.
Here I am getting 3 minus 4, 0. If instead of this I used plus, so it would be equal. So that's why it is wrong. If it was plus, then it will be correct.
Okay. Okay.
Okay, that's the thing. Next question is here. What is this? An orthogonal basis is given. Is it? An orthogonal basis is given here, and I have to find out projection of y on this W subspace, means this one. So it is already orthogonal. So simply we can use the same formula and we will get our answer. I am doing this. One, two, three on 1, 2, 1. So how can I find 1, 2, 3 dot product with 1, 2, 1 divided by dot product we need to use here.
1, 1, 2, 1, 1,
1,
2,
2, 1 dot product with 1, 2, 1. Okay. So if I multiply this with 1,
1,
2,
2, 1.
it will be my answer. So if I do the dot product, what I will get here, 1 plus 4 plus 3, and below it I will get 1 plus 4 plus 1. Okay, so times 1 to 1. So this will be 8 and this will be 6. So 4 by 3 it will be. So I can say that 4 by 3, comma 8 by 3, comma 4 by 3. Okay, this is projection of this y on this one. Now I have to find out projection on this one as well. These two are orthonormal. You can verify this thing. Okay. So if I find out 1, 2, 3's projection on minus 2, 0, 2 and divide it by same this one and then multiply it by, sorry, not this one.
-2, 0, 2.
This is this one. Minus 2, 0, 2 and minus 2, 0, 2. And here if I multiply minus 2, 0, 2. So what will be my answer here? I will get minus 1 and 0 plus 6 divided by 4 plus 4. 8 times minus 2, 0, 2. So
Sir, -2 plus
minus
6,
2
sir.
is this. Yeah, minus 2. I was checking same thing. So it will be 4. It will be 8. I can say that divided by 2 and it will be minus 1, 0, 1. So if I add these two vectors, I will get my answer. If I add these two, so 4 by 3 minus 1, it is 1 by 3. 8 by 3 minus 0, sorry, plus 0, it will be 8 by 3. And 4 by 3 plus 1, it will be 7 by 3. So that's why option 1 is correct. Okay. Yeah.
A little bit one thing that -2 plus 6. computation, like we have been doing only addition there.
Sorry, where? Here. We are not doing addition, we are doing the dot product between these two. So 1 times minus 2 is minus 2, and 2 times 0 is 0 plus 0 here, and 3 times 2 is 6 here. So when I added 6 minus 2, so I got 4 here. And below it, I have minus 2 multiplied by minus 2, that is 4. 0 multiplied 0, I didn't write it. And 2 multiplied by 2, it is 4. So if I add these two, I will get 8 below it. So 4 by 8 times minus 2, 0, 2. So if I reduce it, so it will be 1 by 2, and 1 by 2 if I multiply inside, so I will get this. Is that clear?
Yes, easy, just not practiced.
So any query till now? Anyone else? No? Next is Gram-Schmidt method of orthonormalization. Suppose you are given a basis already like this, and you want to convert it into orthonormal basis. You are aware how to convert an orthogonal basis to orthogonal basis, orthogonal set, you can say set of vector, or orthogonal basis, let's say. Basis into orthonormal. How do we convert this?
Divide by length.
Dividing by the norm.
Yeah, norm, dividing by the norm. If I have u1, u2, u3, so simply divide them by u1's length or u1's norm and u2's norm and u3's norm. This one. Okay. But now if I have to convert it to orthonormal from beginning, means I don't have a basis here. Sorry, basis I am having, but it is not orthogonal. It is simple basis like this. So it is not orthogonal, so their dot product will not be 0. Okay. So what I can do, so basically Gram-Schmidt gave a formula for this. It is this process. I will explain it from here. So what does it say? Let me explain it by myself here. Suppose I have 3 vectors, u1, u2 and u3. Okay, these are just some vector. Okay, these are not orthogonal and neither orthogonal nor orthonormal. So I have to convert them to orthonormal basis, W1, W2 and W3. This is my orthonormal. Okay. And it is some random okay, vectors. So if I want to convert this basis or some random basis. So if I want to convert it into this, so what I will do, U1 will be converted to W1, U2 I will convert to W2 and U3 will be converted to W3. So how can I convert it? Firstly, take first vector, divide it by its norm. So whatever you get, it will be W1. First step is easy. Now next step, follow some pattern. So what I will do, I will take my U2. First step includes removal of its projections on the given one. So W1 we have already find out. So I will remove U2's projection on W1. Okay. So whatever I now got is V2, and now I will divide it by its norm. So now it will become W. This is my step one.
Sir,
Yeah.
we will remove U W1 projection on U2, na?
What?
We will remove the projection of W1 on U2.
No, not W1's projection. U2's projection. We want U2 to convert W2. So I will convert U2. From U2, I want to go here. So from U2, I will remove its projection on W1.
And sir, this projection is the shadow of the vector which
Yeah.
we are removing, na?
Suppose I have a vector here, 3, 4, right? And this is my W1, suppose already 1, 0. So I want the other W2. Okay. So what I can say that I will remove its projection on this W1. So what I will have if I remove its projection will be 3, 0. And if I remove it from this, so I will have 0, 4. Okay. So it will be in this direction. This one will be my W2. It is orthogonal to this, right?
Sir, this projection part is something which I don't understand.
Okay, I will explain it in just some time. Okay, let's complete it. Then I will tell you again once. Okay, once it is finished, then I will tell.
Okay, sir.
So this will be your W2. Next is U3. You are having the third vector. So first step is reducing its projection or removing its projection on this one. So now I have W1, W2, and I want to find W3. So what I will do from U3, I will remove U3's projection on W1, U3's projection on W2. So whatever I have is now B3. And now I will divide it by its norm, and then I will get my W3. Okay. Suppose if I have my, yeah.
Is that U1, U2, U3 are all interconnected to W1, W2, W3?
Yeah, we have to connect them. Means from U1, I want my first orthonormal vector. From U2, I want second orthonormal vector. And U3, I want my third orthonormal vector. What was the problem earlier? Suppose I have a basis like this 1, comma 1 and 1, comma minus 1. Sorry, it is already orthogonal. Let's take some other basis. Suppose I have 1, comma 1 and 1, comma 2.
Sir,
Yeah.
The orthogonality
Yeah.
is like having so, purana topic hai, but I really need help.
Yeah.
Dot product is 0.
Orthogonality means, yeah, the dot product or inner product that you are using should be 0. That's all. If you have two vector A and B and their inner product is 0, so you can say that these are orthogonal. Okay.
Basically, two vectors are perpendicular to each other. That's it.
Not in all cases. When you are using dot product, then they are perpendicular. You can see.
Yes, sir. Normal dot product.
Yeah. Normal dot
Sir,
product.
this
Yeah.
sometimes inner product is also being defined in a new way that makes more confusion.
And it will not be perpendicular. Okay. Geometrical sense and here because it is linear algebra, don't worry about the geometry and that all. But if dot product, then you can conclude that these are going to be perpendicular. Okay.
We don't have to make geometric thinking out of this linear algebra now.
Geometry is not possible. Up to R3 you can represent. Okay, right. First thing is this. After that it will be over. So in linear algebra we will continue. Okay. They are manually defined. Mostly the inner product are some functions. So they don't make that kind of sense that dot product make. So there are some different things. So I took an basis here. Okay, I am going to convert it now. So how will I convert? So firstly, I will take my first vector, divide it by its norm. So on dividing it by its norm, it will be 1 by root 2, 1 by root 2. Right? Now I will take my second vector. This is my W1 now. Second vector, I will find my second vector's projection on this one. So it will be nothing 1, comma 2's dot product with this 1 by root 2, 1 by root 2 times in this direction 1 by root 2, 1 by root 2. Okay, I will not divide by its norm because it is 1. So simply I do the dot product and I will get here 1 by root 2 and 2 by root 2. If I multiply, sorry, plus 2 by root 2. So if I do the multiplication here with this one, so what I will get here 1 by root 2, 1 by root 2. So I will get 3 by root 2 multiplied by 2, 3 by 2 and 3 by 2. I have to remove this part from this vector now, 1, comma 2. So if I remove this, so it will be minus 1 by 2 and 1 by 2. Okay, so it is having some norm that is 1 by 2, I think, or not 1 by 2. Let's check what will be its norm. I will divide it by its norm as well. So its norm will be 1 by 2 square plus 1 by 2 square.
1 by 2.
Okay, so it will be 1 by 4 plus 1 by 4, 1 by 2. So its norm is 1 by root 2 actually. So if I divide it by 1 by root 2 means multiply it by root 2. So it will be minus 1 by root 2 and 1 by root 2. Now you can see both these W1 and W2 are orthonormal. They are length is 1 and they are perpendicular to one another. Because we are using dot product, so I can say that they are perpendicular. Okay. So this is the way. Here you can see the steps involved. You have some basis like this. You want to convert it to an orthonormal basis. So what you can do, W1, firstly take the vector V1 here and simply divide it by its norm. So you will get this vector. They used other kind of notation. I used U1, U2 here, and they are using it here. Okay, so don't get confused. Okay, next is W2. W2 is what? W2 it is taking after removing its projection on U1. U1 is this vector on orthonormal. Okay, so remove this vector's projection on this vector, and whatever you got, it is W2. And if you divide it by its norm, now you will get this second vector. So how can you get your third vector? Here, the third vector. So firstly, take a third vector from here, find out its projection on this vector and on this vector as well, and remove it. So V3 I took from here and I removed its projection on U1. Then I removed its projection on U2. So whatever I got is W3, and on dividing it by its norm, I will get my U3. So in this way, you can go on. The n vectors are there, so you have to do it after that. Is that clear?
Yes, sir. So now we may discuss about projection.
Yeah. So what was?
So this projection.
Okay, you want the projection. Okay. So projection basically, if you have a vector V here, and you want its projection on A, so it is nothing but you want this part. If you drop a perpendicular from here, in case of dot product, I'm saying, so it will be nothing but suppose its length, this B vector's length is this. I can denote like this. Okay. So it is a triangle that has this angle theta, right angle triangle. So you know that what will be this side? This will be B cos theta, magnitude of B times cos theta. So how can I, this vector's magnitude I got now only. Magnitude I am having, or the length I am having. This is the length only. I want this direction as well because I want to convert this length into vector. So how can I convert? This direction is same as A direction. So I will find out a unit vector in this direction A. So I will multiply it by A vector divided by A's magnitude. Okay. So what I can say that now, this B vector cos theta, you know that if you are aware that A vector dot B vector is nothing but A's magnitude times B's magnitude cos theta, or length of A times length of B cos theta. So this B cos theta I can get as A dot B by A's magnitude. So I can remove this and write here A dot B divided by magnitude of A. So you know that A dot B, I can rewrite it A dot B, A vector here, and AA. So it will be magnitude of A square. So what is this? If I do A dot product with itself, so it will be equal to this. So I can say that it will be A dot A. Or if it is inner product, so you can use here inner product directly. Okay. Is that clear?
Quite not. This A dot B, this was not explained in the course now. This A dot B equal to AB cos theta.
This one?
Yes, sir.
It's done in the projection lecture.
This part is actually when you use whenever you find out the angle between two vectors, so we use this formula, if you are aware of this.
So it was also given in the lectures also.
Yeah, it is in the lectures as well.
Sir, what is about, like, he is confused about the what is projection, I think.
Projection is nothing but if you are using dot product. Okay, in case of dot product, I am telling. So it's you can say shadow. Suppose you are going somewhere in two-dimensional plane. You are having a two-dimensional plane here, and you want to reach to this point. Okay, so one way is to directly go from here to here. Another way, suppose you don't have a direction. This direction you are not aware, but you know one direction here and one direction here. You have a compass that can tell you that either this is north, and you can go east and west, and sorry, not this west, south, west. So you have a compass that can tell you a direction. So you can't directly go in this direction. You can go in these two directions or these two directions. So what you can do, you can continue in this direction as long as just reach a point where you only need to go in this direction only. After which you don't have to continue in this direction. So the point at which you are going to travel, up to which you are going to travel, it will be the projection.
So these points, we need to just have to calculate cos theta against the perpendicular
Yeah.
basis.
Perpendicular basis, yeah. This vector times cos theta. It is the projection. So if you want its projection on this one, so it will be up to that point till you have to go in this direction, after which you only have to go in this direction only. So this vector that I formed here, up this one, is the projection of this vector on this. Is that clear now?
So this how this AB cos theta came.
Okay, this AB cos theta. This this is a formula for dot product. It is given already. Okay. So now I said that from this figure, so this vector that I have, so this is a vector. Okay, so it has two things. One is length and other is direction. Okay, length
Yes,
I
sir.
got by this formula, that this is a right angle triangle. So what is cos theta in right angle triangle? So it is theta. So what is cos theta? Cos theta is nothing but this side upon this side. So this adjacent side upon hypotenuse. Adjacent side, I can say that from this formula, adjacent side is nothing but cos theta times hypotenuse. What is hypotenuse? It is the magnitude of B. And what is cos theta? So this side is nothing but B cos theta. And this B cos
Yes.
theta, I computed from this formula. I wrote it B cos theta as A dot B divided by this A, length of A. Okay, I got this. And now if I multiply it with this is the direction. I want only the direction, not any magnitude. So I want a unit vector in this direction, means whose length is 1. So A vector I am having, and I want to make its length 1. So I can divide it by its length. Okay, suppose it is 5, 0. And if I divide it by 5, so it will be 1, 0. Its length is now 1. So that's the way I divided it to convert it into a vector. And after that, I have this, and A dot B is written like here, and the magnitude square is nothing but this formula. So I can write it here. Nothing. You don't need the derivation. Okay, if it is not still not gettable, then don't worry. Just need the formula. But if you want to learn, then you can tell me.
Sir, I got this B cos theta in this side, but the dot product was previously defined as summing a product of the sum of respective entity. Na? So,
Okay,
but this
okay,
is
okay.
cos theta.
Listen. If a vector is given in this way, if a vector is given in its component way, this is your A1, A2, and this is your B1, B2. So dot product is you can find out A1, B1 plus A2, B2, right? This is the way you find out the dot product between these two. But suppose if this is not given, components are not given, only length is given. Okay, length is given,
Yes.
and the
Angle.
direction is given.
Angle.
Okay, yeah, or angle between these two vectors, you can say angle is given. So how will you calculate that time? So then we use this formula. Angle is here, that I will use cos theta, and A dot B is there. Is that clear now?
Sir,
Yeah.
why cos theta is used in this?
Okay. Let me make it here. Suppose this is your first vector x1, y1. You have another vector here, x2. Take it here. I will explain this concept. Okay, right now let me continue my lecture, and then I will explain it in the end. Okay, stay in the class. I will tell you about this, the theory behind it, using this formula, and that I will explain it. Okay. For now, let's continue.
Okay, sir.
Next key part is this. W is a subspace that is given with respect to inner product R4, and dot product we need to use. Okay. So three vectors are there, ordered basis for W. Okay. Where V1 is this, V2 is this, and V3 is this. So now you have to use the Gram-Schmidt method for orthonormal basis. So you know that the orthonormal basis, so you can continue. So I have already solved it, I think. Let me open that part. Okay. So that I don't have to solve it again. Let me show, explain it directly from there. Yeah. Here it is. Okay. So you are given this U. These are your three vectors. Okay. Three vectors are there. And you want to find out your W1, W2, and W3. So W1 you can directly get by dividing it by its norm. So I divided it by its norm. Norm is 2. So I divided by 1 by 2. So I got this vector. Now I want my W2. So firstly I find out V2. So how can I get V2? I removed the projection of U1 from U2. Sorry, I removed the projection of U2 on W1 from U2. It is U2's projection on W1, and I removed it from U2. So after removal, this is the projection that I got, and I removed it. So I got this vector. Okay, now I have to divide it by its norm. So on dividing it by its norm, I got this value. Okay, this is the norm you can see to find out using this root 3 by 2 was the norm. So on dividing this vector by root 3 by 2, I got this.
Sir, we can find the orthogonal first also, and then also at last convert it into orthonormal, right?
Yeah, that's fine. Yeah, that's fine. You can also do that. But what is the problem there? Now here you find out the projection directly, that do the dot product and multiply by W1. Okay, but that time you have to divide each time by its norm.
Yeah. Well, the process complicates. Yes, understood.
Process complicates there. Okay, so that's why if you can, it is up to you. Whichever
But
way.
in this one also, like you have to convert it to orthonormal, right?
Sorry.
In this one also, you have to convert it to orthonormal at last.
Yeah, in this one we are every time. No. We are in this one we are already converting it. These are orthogonal already, and we are dividing by its norm, so it is converting. But when you are using that, only removing the projection, not doing divide by norm. So you have to do, suppose in the next step, what you have to do here, you have to divide it by W1's norm, here by W2's norm, square. Okay. And then you will get your projection. And in the end, you still have to divide the first vector by its norm, second vector by its norm, and third vector by its norm.
Sir, in this one, in V2, the one which you are getting 1 by 4, 1,
Yeah.
1 minus 3. Okay, you are dividing it. Yeah, correct. That's what I told. Okay, you are dividing it again, right?
This is your V3. In V3, how do we find out? I will subtract U3's projection on W1, U3's projection on W2 from U3. So after removing this projection, I got this vector. So now I will divide it by its norm. So its norm will be root 2 by root 3, I think. Yeah, root 2 by root 3. 4 plus 1, 5 plus 1, 6, 6 by 9, 2 by 3. Yeah.
Yeah, sir. Actually, this is only what I was telling. So this V3 is basically the orthogonal one, right?
Yeah, it is orthogonal. It will be orthogonal to these two vectors, W1 and W2.
Correct.
But if you divide it by its norm, then it will be
orthogonal.
So this is the way you do.
Sir, and V3 is, can you just go back one, sir? Sir, V3 will also be orthogonal to V2, right, sir?
Yeah, of course.
Yeah. Okay, correct. Got it.
Orthogonal to this.
Yeah, sure.
Okay.
Sir, I want to ask one question.
Yeah.
Sir, exactly what was the plan to get into the 16th examinations? Will we getting any trainings for that?
Sorry, I didn't get, means what kind of training?
As if 16th is our quiz to examination.
Yeah. Of course.
So, any continuation with PYQs from tomorrow onwards?
Okay, yeah, I will do it. I will solve one of the PYQ on Friday and Saturday. I will take 2 revision sessions. So in that way, I will solve. From instructor session, maybe ma'am or sir will do something, but from TA session on Friday or Saturday, I will do PYQs.
Sir, can you please tell which papers you are going to take?
Last two semesters, I
Last
think,
one. Okay, fine.
last two maybe. And if they are solved by instructors, then I will take some previous one.
Sir, from tomorrow onwards, we will be like focusing over the quiz too, na?
Yeah, from after that, because today week 8 will be completed, and after that I will make one revision, and then PYQs we will solve.
Okay, sir.
So next part is this one. So after this solution, so we got our basis like this, orthonormal basis. Okay, I have a vector A, inner product space with the dot product we are using. So I have some space like this. So it is saying that which of the following is a basis of W. So you can see that we have to use dot product here. It is saying that W is a vector space that has all the vectors such that this equation is to be satisfied. It is not an equation looking like, but it is. If you multiply these two using dot product, it will be 2 by 3x plus 2 by 3y plus z by 3 is equal to 0. It is z. So from here you can get 2x plus 2y plus z is equal to 0, right? So this is an equation of plane, right?
Yes, yes.
We
It
can
has
write
one.
z equal
And we
to.
can put the values and see.
Now here we have 3 variables, so I can write any one in the form of other two. Suppose I am writing z as minus 2x and minus 2y. So I will give randomly two values. So let's see in these options what are given. So x is taking 1, 1, minus 1 and 1. So let's give value 1. So I am going to give x value 1 and y value 0. Most of the options has y value 0. Okay. So I will give x value 1 and y value 0. So x when I am going to give 1, so minus 2, and y if I give 0, so nothing. So minus 2 is the value of z. X
Yes.
value minus 1, y value 0, and z value minus 2. Okay. Okay. So next is, sorry, I wrote something wrong. X value I give 1. Okay, x value was 1 and y value gave I 0. So now it is looking like this option, right? So I will check this part as well. X value 0 I will give and y value 1 I will give. X 0 and y 1. So z I will get from here minus 2 again.
So we can directly put the values and check also, right, on the plane equation.
Yeah, you can also do that. So you got this vector. Yeah, you can do that thing. You can take these vectors and you can put them here. But it is asking for basis. Make sure that these two vectors are linearly independent.
You got it, sir. Got it. Yeah, that has to be taken care of.
That has to be taken carefully.
Correct, correct.
Otherwise, it will cause problem. Okay.
Right.
So this is the option, right? Okay. But now in this one, you can see minus 1 to be given to x. So if I give value minus 1 here, so z value will be 2 in this case. 2. And if I give value 0 and minus 1, 0 and minus 1 here, so minus 1 here, and it will be plus 2. So this is matching with this part. Basically, if you look at these two values, so it is a multiple of this and it is a multiple of this. If I multiply it by minus 1, I will get this. So these two are bases. Is that clear? Okay. Next is consider a set W that has only one vector, this one, from the inner product. It is saying that find the dimension of subspace W is perpendicular, means all those vectors that are perpendicular to this. So you know that it is a three-dimensional, or it has three components. So it is a vector in R3 vector space, right? So R3's dimension is 3. And if I find out span of this W, so, or if I say that what will be the base dimension of span of W? Dimension of
One.
span of W. So it will be 1. So remaining 2 dimensions are there. 2 dimensions are still remaining. So it is asking find the dimension which are perpendicular to this. In this sense, perpendicular means the same thing, that how many dimensions are remaining, how many linearly independent vectors or orthogonal vectors I can have in my space. So if I have, you can see here, if this is my three-dimensional space and I have one vector here, suppose, okay, so I can have one here that is perpendicular to this too, and if I can have one vector here that is perpendicular to this and as well as this. Okay, so two vectors are still remaining, so I can say that dimension is 2. Or one more thing you can do, if you want to solve it by algebra, not by geometry.
Sir, can you explain this again, this question, please?
This question, yeah, I am explaining it. Okay, first way is this, that you have 3 dimensions here. So suppose your first vector is in this direction. So how many vectors you can put here that are perpendicular to this? So if I put one vector here, right, and I can put here one. So this is perpendicular to this, and this one is perpendicular to both of them. So only 2 vectors I can put, that can form this dimension. Dimension means they should be linearly independent of one another. So they are. So 2 dimensions are remaining. Or one way is this, if you want to use the linear algebra method, that which vectors are perpendicular, whose dot product with this will be 0. Suppose I have all the vectors x, y, z. If I do dot product with this 1, 1, 1, and if it is equal to 0, then I will have all those vectors, I have all that space, okay, where I it is sorry, the equation that I will get from here, it will be the equation of that subspace that is perpendicular to this subspace. So what I will get here, x plus y plus z is equal to 0. So you can see that it is an equation of plane. So what will be the dimension? Dimension will be 2 here directly. Is that clear?
Yes, sir.
Anyone else having any doubt?
Sir, so this two perpendicular.
Clear.
Can you explain once?
Which part? This one, linear algebra method.
This one is okay, sir. This the one previous, this one, yeah.
Okay. In this one, it is saying that we want all that subspace, its a dimension that is remaining, or I can say that that is perpendicular to this.
Okay.
Okay, so if I have a vector here in this way, so I want all the vectors that are perpendicular to this. So if you look here, if I have this line, whole line, so I can have this plane here, this plane.
Okay.
So any vector if I take in this one, so it will be perpendicular to this vector.
Okay. Okay.
So this is a plane. So what will be its dimension?
2 dimension.
That's why I put here. Okay. That's the case only. Anyone else having any other doubt? No. Next is orthogonal transformation. We have seen the linear transformations. Okay. So now it is time for orthogonal transformations. So what are orthogonal transformations? Basically, they are nothing. They should satisfy this equation. If you have 2 vectors in your domain space and you want their transformation of TV and TW, and you then do the inner product of them. So it should be equal to the inner product of those vectors. These are the images of that vector, and if you do the dot product or inner product after that, it should be equal to the inner product previously. Then
Sir,
you can, yeah.
in this one, I'm sorry, huh? So, sir, in this one, V and W can be any kind of vectors, right? They can
Yeah.
be orthogonal as well as they can be non-orthogonal, right?
Yeah, right.
Okay, okay. And in case if V and W will be orthogonal, then
Yeah.
definitely the dot product will be 0, right? The standard dot product will be 0.
It will be 0 as well as this will be 0.
Okay.
We are
Sir,
using dot product. Yeah. Yes.
okay, okay. And the angles and the norms will be preserved, right?
Yeah.
Okay. Sir, just wanted to ask, like, why is it called orthogonal transformation? In case of orthogonal vectors and all, it's understood, but in case of normal vectors, like just because it preserves the product, that's why.
It actually not preserves orthogonal. Yeah, you can say that it is orthogonal because it preserves the product. Even after image, you are finding the image and then doing orthogonality. Still, it is orthogonal. If it was earlier orthogonal, then it is still orthogonal. So that's why transformation is still orthogonal.
Okay. Okay.
That's why we say that.
So
And
can you show an example with two non-orthogonal vectors? It would be great.
okay, two non-orthogonal vectors.
Exactly. Yes.
Um, let's take an example. It must be given here already. Let's check.
Okay. Okay. Fine. Fine. No problem.
Here it is given. Okay. In this example, I will take this. So transformation of x comma y is given like this. It is a vector in R2, and I want to check this part. So I will do the inner product of first vector is this one, second is this one, and find out that what I will do, I will find out their transformations firstly. So what will be the transformation of this one? It will be this, right, from this formula. And the transformation of this will be this, right, from the same formula. So now if I do the dot product, we have to use this dot product. Inner product is not defined, so dot product we will use. Okay. So if I do the dot product here, so x plus x1 plus y1 divided by root 2, it will be multiplied with this part, this one with this one, and the next one will be with this one. So this is here, you can see. After doing the product, so I got this part. So from here I can cancel out the same values x1 y2 and x1 y2 with different signs. Okay, y1 x2, so this will be cancelled out and rest will remain same. Okay, so it will be equal to this x1 x2 y1 y2. So you can say that it is equal to the inner product of these two, or dot product of these two vector, earlier vector. Without transformation, if I find out the dot product, it will be same as this. Now if you want to take an example, you can take like 1
Understood.
comma
So
1.
it would
Yeah,
satisfy for any vectors. Okay. Got it.
now it will.
But only this transformation would satisfy, right? Not any other.
Yeah, not all are going to
Not all
satisfy
are going to satisfy. Okay. Okay.
this. Next, it is given inner product from R3 to R2 with a dot product we have to use, and transformation is given like this. So we have to show that it is not orthogonal. So simply you can take some random vectors and you will try to figure out, or one thing you can do, you can take general case and then you can try. So figure out if it is not coming equal, then you can directly imply. Suppose I am taking a vector x1, y1 and z1. So if I find out its transformation, it will look like x1 plus y1 plus z1, and below it, it will be x1 plus y1. Okay. And I will take my second vector as x2, y2, z2. So it will be here its transformation, x2 plus y2 plus z2, right? And below it, I will have x2 plus y2. This is x. Okay. So if I do the dot product here, so it will be equal to x1, x2 plus y1, y2 plus z1, z2. So it should match with this right hand side. So if I do dot product here, so what I will get here, x1, x2 plus x1, y2 plus x1, y, z2, sorry, z2. Okay. And then I will have y1, x2, y1, y2 plus y1, z2. Then I will have z1, x2 plus z1 and y2 plus z1, z2. Okay. Then I have to add their product as well. So it will be again x1, x2, right? It is already there. Again, it is coming. And then I will have x1, y2 and y1, x2 plus y1, y2. So you can see that if I add this, still I am not getting this. It has some other terms as well. This is matching, and this is matching. These other terms are not being cancelled out, and they're still remaining in this part. So it will not be an orthogonal transformation. You can take
Sir,
some, yeah.
in this one, so you have first taken transformation of t x1 y1 z1, right?
Yeah. I took a vector u and took its transformation. Then I took a vector v and took its transformation and did the inner product. Okay. and calculated. I got this.
Okay, and you check the inner products of V1 as well as E and B also.
Yeah, I check it with this one, this part.
Okay, it's not matching basically.
It's not matching, so that's why you can disagree, or you can say
Okay,
that
this
it is.
particular transformation is not a orthogonal transformation.
Yeah, exactly. Okay. Next is rotation matrix. What are rotation matrix? Basically, we rotate it. Same way here, the orthogonal transformation that we are reading or studying. So rotation matrix is related to this part a little bit. So you can say that suppose you are having a two-dimensional plane and you want your plane to be rotated. Means each vector, suppose your first vector is here. So if you rotate it by theta, suppose this is your image of this vector. When you rotate this vector by theta, so it is your image, and this was your earlier vector, original. So it was its image. So this is called theta, or you can say that it is rotation, or you can say now it will be orthogonal transformation in this case. Okay. So how do we find out? It's a matrix for this, matrix for linear transformation, as we find out. So now we will find out for this. Okay. So I will take some standard basis and then I will find out. Suppose this is 1 comma 0 and this vector I am taking is 0 comma 1. So you can see here, if you observe carefully, that this vector earlier it was 1 comma 0. So it has a length 1, right? And if I rotate it, so its length will be preserved. So now here its length is 1 still, but it is at angle theta. So if I find out its coordinate now, so what will be those? So I can say that this part I need to find out. So what will be this part? It will be nothing but
Cos theta.
cos theta, right? Okay. And what will be this part, this y coordinate of this point? It will be
Sin
sine,
Sine
sine theta, right? Okay. This is for 1 comma 0. Now let's remove this. Now take 0 comma 1 because it has two vectors in its basis, two linearly independent vectors. Suppose this was my 0 comma 1, and if I rotate it, I am rotating anti-clockwise. Okay, so it will be here. I will tell you what happened when we rotate it clockwise. So here I will have this vector cos theta. So now if I find out its projection here, so what will be that? It will be nothing but its y coordinate will be cos theta, right? You can see it is a triangle and its length is also 1. So this part will be cos theta. And what will be this part? It will be sine theta, right? No, it will have a minus sign here. Why I am saying so minus sign? Because it is lying on the negative axis, negative x-axis, right? This theta I am using here, but actually I don't, uh, yeah, I can use this here. Okay, so I want this coordinate here. So its length is sine theta, but if I want to find out its coordinate, so I have to put the sign as well. Is that clear? Its length is sine theta, but we have to put the sign. So I got transformation of 1 comma 0 as cos theta comma sine theta, and transformation of 0 comma 1 as minus sine theta cos theta. So if I rewrite this, so as a linear combination of these two bases, suppose same basis I am using for domain and codomain. So what will that be? Cos theta times 1 comma 0 plus sine theta times 0 comma 1, right? And here I can say that minus sine theta times 0 comma 1, sorry, 1 comma 0, and plus cos theta times 0 comma 1, right? So now if I form the matrix, I will write the first column as first row, that will be cos theta minus sine theta, and then second row sine theta cos theta. So this will be my matrix. It is called rotation matrix. Any query till now? No? You can see here cos theta minus sine theta here and sine theta cos theta here. Now we can take standard cases from this part. Suppose instead of rotating it anti-clockwise, if I would have rotated it theta clockwise. So if I'm rotating it clockwise and I want to measure its angle according to this x-axis, so I can say that it is rotated by minus theta. So when I'm rotating it theta wise, so my matrix was this. But if I rotate it by minus theta, so how will my matrix look like? Cos minus theta cos minus theta minus sine minus theta sine minus theta and cos minus theta. So if I do this, so what I will get? Cos theta sine theta minus sine theta and cos theta. So it is nothing but transpose of this matrix. Earlier matrix, what it was, it's just its transformation. Not transformation, transpose it. Okay. So if it is my projection matrix, so not projection, it will be my transformation matrix. So A, let's say A. So it will be equal to A transpose. If I use minus theta here. So same thing is explained here. You can see rotation of theta. If you are using theta angle and you are rotating it by theta, so its transpose, if you do, it will be equal to rotation matrix when you use minus theta. Okay. And if you multiply both these matrices, so what you will get here, if you multiply these two matrices, so cos theta times cos theta, cos square theta, c square theta, and minus sine theta, it will be plus sine theta, sine square theta.
Identity matrix.
Next element will be this row multiplied by dot product with this column. So it will be cos theta sine theta
Minus sine theta cos.
minus sine theta cos theta.
So you are multiplying the transpose, right?
Yeah, multiplying it by transpose. A times A transpose I am doing. Next is sine theta. If I multiply it by this, so what I will get here? Sine theta cos theta. Okay. And cos theta minus cos theta sine theta. And if I multiply this second row with second column, I will get sine square theta plus cos square theta. So this value is an identity. You can see that it is 1, it will be 0, it will be 0, and it will be 1. Okay. So what I can conclude from here that if I multiply this, so I will get an identity matrix. If I have done vice versa as well, so I will still get this identity matrix. Okay. This is a case for 2-dimension or in R2 space. Suppose if I am going to rotate in R3 now. I have a 3-dimensional space and I want to rotate it now. So earlier I have only one choice, that I have to rotate in this direction. Okay, okay, you can say that 2 choices I am having. This is negative, so I'm not including this part. Okay, just only one direction I am having to rotate it. But now suppose I have this part and this value, this here. I keep my x-axis, this is x, suppose this is y and this is z. So if I keep my x-axis fixed and I rotate this value like this plane I am rotating. Okay, so all my matrices only z and y coordinates will change and all other remains same. Okay, so you don't have to calculate it like this by finding out 100s what will that be and that be. You can directly say that the previous matrix that I got for R2, because one axis is fixed, okay, other two are changing. So when two matrices, we are rotating only one plane here. You can see YZ plane is being rotated. So first column is for X, second is for Y, and third is for Z. So what I can say that first will remain same. So 100 and 00 I will put, and these two will rotate. So here I can say that cos theta minus sine theta, and cos theta.
Sir, in this case, basically, we always go by taking the standard basis, right?
Yeah, mostly standard basis. So this is my rotation matrix when I kept my x-axis fixed. If I keep my y-axis fixed, so what I have to do, I have to write down the matrix like this: 0, 1, 0, 0, 0. Okay. So now remaining part will be my rotation matrix of for R2. What was that? Cos theta, then minus sine theta, then sine theta, and then cos theta. Okay. Next is rotation matrix with respect to theta 3. So what will be that be? Z axis will be fixed 0, 0, 0, 0 here. And this two-dimensional matrix I will represent here. Cos theta minus sine theta, cos theta. Okay. So these are the three metrics that you need to keep in mind. Which axis is fixed, and or you can say about which axis you are rotating. It is rotating about y-axis, so this matrix is there. So if it is rotating about x-axis, so this matrix, and z, this matrix. So what you can now figure out, you can see again that if I multiply this r theta, any one of them, with by its transpose, okay, so it will be an identity matrix. Okay, you can directly see this. If I multiply this part, I am doing it for x, you can solve it for these two, okay, by yourself. So if I multiply it by 1, 0, 0, 0, 0, and cos theta, sine theta, and sine theta minus sine theta, sorry, cos theta. So what I will get here, first row multiplied with first column, it will be 1. First row with second, 0. First with second, 0. Okay, this entry. Second row with first column, 0. Second row with second column. So cos theta, and minus sine theta, it will be 1. Okay. For second row and third column, it will be 0, 0. Okay. Cos sine theta, cos theta, sine theta, and minus sine theta, cos theta. So 0. And if you multiply it by 0 here, sorry, third row with first column, so it will be 0. Third row with second column, so 0 multiplies 0 is 0. Sine theta, cos theta, minus cos theta, sine theta, so it will be 0. And third row with third column, 0, 0, 0. And sine theta multiplied by sine theta is sine square theta. Cos theta multiplied by cos theta, it will be cos square theta. So sine square theta plus cos square theta is 1. Okay, same for this. But what you need to keep in mind, one extra thing, that if it is this, okay, so suppose I am representing it by r instead of using this theta, simply I am representing by r times r theta, sorry, r transpose is I, as well as r transpose time r is also I. If I find out now its determinant, what will be my determinant for r transpose? It will be equal to determinant of I, right? Both side I am taking the determinant. So you know that I can write this determinant of r times determinant of r transpose is equal to determinant of I is 1. Okay. Determinant of r transpose will be same as r, right? So I can say that it will be determinant of r square is equal to 1. So what will be the determinant of r? It will be equal to plus
minus
or
1.
minus. If in examination this question is asked, so what you can do, you can directly write the determinant of r transpose will be 1. Okay, but determinant of r will be plus or minus 1. Now you can verify this thing from here. Okay, let me find out the determinant for this third one. Okay, it is visible from here. So let's say I am finding out with respect to the third row. So this is 0, 0, 1. So I can see the 1 time.
Sir, just a second. Sir, like even in case of, say, for example, it's a 2 by 2 matrix,
Yeah.
then also r equal to plus minus 1 is applicable, right?
Yeah, you can check. It will be.
Okay, it will be. Even if for any orthogonal vector, yes, we can take 1, 0, 0, minus 1. Yes, we can do that.
Okay. Yeah. So let's move. 1 times it will be determinant of cos theta minus sine theta, cos theta. So if I find out determinant, it will be cos theta, cos square theta minus
Plus
sine.
minus minus sine square theta. So it will be plus sine square theta. Okay. So that will be equal to 1. In this case, the determinant is 1. But if I find out determinant in this case, so with respect to second row, I have to find out. So if I use second row, so it will be This entry should be plus, this will be minus, and this will be plus, right? When finding determinant.
Yes,
So
sir.
minus 1 times determinant of cos theta minus sine theta, cos theta, right? So its determinant we already find out it is 1. So minus 1 times 1, it will be minus 1. Okay. You can verify for this matrix. It will be 1. Okay. So this is the thing. Now let's see what are orthogonal matrices. Orthogonal transformation you are aware. Now matrices. So what is orthogonal matrix? It is nothing but when any matrix satisfies this condition. Okay, then you can say that it is orthogonal matrix. So you know that rotation matrix satisfy this part. So rotation matrix are orthogonal matrix. That's it. Okay, it is up to your week 8. So now let's see some questions. Any query about the concept anyone is having? No. So let's continue with this. So here you are given R2 to R2 be a linear transformation if this condition holds.
So that
It
is
is
for
not.
orthogonality.
It is orthogonality, orthogonal linear transformation. Okay, orthogonal but linear as well. Okay. Next is this one. In this one, it is saying that TR2 to R2 is a linear transformation where R2 is an inner product space and you are given inner product of two vectors like this, and then it is given this. So it is not going to be linear, it is going to be orthogonal. Okay. If this condition I said, this condition holds, so automatically you can put orthogonal linear transformation, the same option here. Any problem in this?
Sir, we will have to assume that this inner product is a valid space.
Yeah, it is given already that space with respect to the inner product. It is already concluded that it is inner product.
Okay.
Okay, otherwise it will say that it is some function or it is some kind of product only. So check that whether it is inner product or not.
Okay, sir.
Okay. But now here it already concluded that it is inner product, so we don't have to check, right? Next is this one, 159 question. So here we are given A and B are orthogonal matrix of order 3. Then A and B are equivalent matrices. Okay, if these two are orthogonal matrix, so what was the
They should
problem?
be true.
Yeah, B is equal to QAP, right? So as you know that if I multiply A by its transpose, it will be its identity matrix, right?
Yes, sir.
Okay, identity matrix it will be, and if I multiply it by B, so it will be equal to B. Is that clear now?
Sir, but here we dealing with square matrix. It's not required, no? So,
Sorry.
sir, in equivalent matrices, we are not dealing with square matrices, no?
Here we are dealing with square matrices. In orthogonal matrix, wherever you are going to do, so you have it, and these are going to be
Square matrix.
square matrix. Or why do you have to take square matrices? Let's say it is not square, then what is the problem in that?
That A into A transpose will be a problem.
And but here it is already given, order 3. So you have the choice, okay?
Sir, in this one, in this one, how did you take, sir, P as A transpose? Can you?
Okay. I am aware of this thing that A times A transpose is I.
Correct.
So I am aware of this part. So I know that I can write B is equal to B. Okay, so if I multiply it by I, so it will be same as this. So simply I removed it and took A transpose. So it is matching with this part. Just some kind of a thinking, the concept that I am aware, I just applied this part.
Okay.
Okay. No pre or no other formula I used. Just a pre-knowledge of this concept. That's why I used. Okay. A and B be orthogonal matrix, then A and B are similar. No, it is not, because we can't say that this B will be A transpose inverse. It is not always possible. Okay, so that's why this is wrong. In this part, we can apply this, but we can't say that B will be inverse of this because it is not possible. Maybe we are having different types of uh, orthonormal vectors inside them. So that's why. Next is AB, a rotation matrix corresponding to anti-clockwise rotation with respect to XY plane. Okay, of the XY plane about the Z axis. So Z axis will remain fixed and other two will change. So it is saying that then the nullity of matrix A is 0. Yeah, we find out its determinant. What was that? 1,
Correct. 1.
right? If the determinant is 1, so nullity is 0.
Yes,
Non-zero.
unique
Yes.
solution.
Unique solution.
Next is this one. A is a rotation matrix corresponding anti-clockwise rotation of the xy plane about z-axis with angle theta, and B is a rotation matrix corresponding to the anti-clockwise rotation xy plane about x-axis. This is about z and this is about x. Then A and B are equivalent or not? Okay. So I have to say that I have two matrices, and you know that if I can derive if I can form one matrix, if I can form B matrix from A by using some elementary row or column operations, okay, then I can say that it is equivalent, right? Week 7 concept. Or we can say that if rank are matching, then they are equivalent. So rank of B is equal to rank of A, right? Because both have the determinant 1. So
Yes.
rank is full, rank is 3, and rank is 3 in this case.
Sir,
So
for
we are
equivalent rank has to be same, ना उल्टा नहीं है ना?
sorry, what?
Sir, is it that rank has to be same or for equivalent the rank has to be same? But if the rank are same, I think I'm forgetting it.
Let's see some properties if it's characterization. Two matrices A and B are equivalent if A can be transformed to B. Okay, and two matrices are equivalent if rank of A is equal to rank of B. So two methods are there.
Okay.
So that A and B are equivalent, we have to show that. So firstly, we will transform A to B. We transformed it, or we can use this method. Rank are matching, so they are equivalent. We concluded that part. We are not saying that if it is same, then still it cannot be. It will be. If rank are matching, then it will be equivalent. Okay.
Yes, sir.
So can you repeat again if you don't mind, please? Yeah.
If any of these two conditions satisfy, then it will be equivalent. Two matrices are equivalent. You can see what are those. If A and B are equivalent, if A can be transformed into B by elementary combination of row or column operations.
Okay.
Okay. Next is if two matrices A and B will be equivalent if their rank are matching.
So, sir, if any one condition is satisfied, then we can say that it's equivalent.
Automatically second condition will be satisfied. Okay. If one is satisfied, then
Yeah,
automatically
understood.
one you can check. Rank checking is easy. In most of the cases, you can apply that. Okay. So here we are. So that's why this option is correct, because both have the rank full. Okay. And if you want to check whether you can form other matrix using some elementary row operations or column operations, then you can apply that.
So, sir, a small doubt है sir. When we read about that equivalence of matrices, then
Okay.
we said that if one of the matrix can be represented as Q, let's say B is the matrix I want to represent in terms of A, then B equal to QAP. If
Yeah.
that happens, then we
Yeah.
say the both are equivalent.
Yeah.
Sir, if this condition happen, then I can say that rank has to be same. But if the rank is same, will this condition happen? That's the doubt, sir.
Yeah, then it will also happen because we have seen one thing that it can have multiple solutions. A lot of solutions are possible in that case. This P and A and B are there, then this P and Q are not unique. They can be a lot of
Yes, yes,
matrices.
yes, yes. They can be
Okay.
different.
So
Yes,
at least there will be one matrix that can form it equivalent.
yes, sir.
Okay, we
Thank you,
can
sir.
find out it. So that's why it is. Okay. So any other query?
No, sir.
So question 160 here. So it is saying that representation of orthogonal transformation, choose the correct set of vectors. Okay, there is an orthogonal transformation. So what I can say that, what are orthogonal transformation?
The inner product of the vector should be same as the inner product of the transformations.
I have a basis. Okay. Suppose my basis is orthonormal. Okay, suppose I have a vector, any vector. So if I find out V1, its transformation, so it will be some vector. Okay. Suppose it will be W1. Okay. And transformation of V2, it is W2, and transformation of V3 is W3. So you know that if I do inner product of these two, it will be equal to this. So if they are orthogonal or orthonormal, so what I can say that orthonormal they are, so it will be 0, means these two are also orthonormal, and
Yes,
these two will be, and these two will be. So if I represent this W1 as linear combination of these three, so suppose alpha times V1 plus
Can you
beta
repeat
times
that part?
alpha 1, alpha 2, V2 plus alpha 3, V3. Okay, here I will represent alpha 2, V1 plus, sorry, beta 1, beta 2, V2, beta 3, V3. And here if I represent it as gamma 1, V1, gamma 2, V2, and gamma 3, V3. So here you can see I transformed three vectors and their transformation is look like this. Okay, and if they are already orthogonal, suppose orthogonal, okay, or orthonormal, let's say normal, it will be easier. So if they are orthonormal and if I find out its transformation, so it will look like this. Okay, so if I do the dot product of V1 and V2, so it will be 0, right? And V2 and V3 if I do, it will be 0, and V3 and V1 I do, it will be 0. And length of each vector, V1 is equal to length of V2 is equal to length of V3, it is equal to 1. Orthonormal they are. So here you can see, if I represent it as a linear combination of these vectors, so what would that be? So if I do dot product of row 1 with row 2, these two dot product if I do, okay, so what would that be? So you know that I have to do the dot product of this with this, and this. Okay. So if I do V1, V1, so it will be only the dot product will be here done. Here V1, if I do with V2, so it will be 0 and it will be 0. So what I will get here, alpha 1, beta 1, and V1 square. Now I have to do the dot product of this with this, and this. So if I do V2 dot product with V1, so it will be 0. Okay, and here V2 with V2, so I will get here alpha 2, beta 2, and V2. From here I will get alpha 3, beta 3, V3's square. So this is the value I am getting, and I am doing what I am doing here, transformation of V1's dot product with transformation of V2 I did. Okay, so it should be equal to V1 dot product V2. What is that? 0. So it should be equal to 0. So from here, I know V1's length is 1, right? So this is 1, this is 1, this is 1. So what I got, alpha 1, beta 1, alpha 2, beta 2, and alpha 3, beta 3 is 0. Right?
yes, sir.
Means the vector, if I represent alpha 1, alpha 2, alpha 3, and if I represent beta 1, beta 2, and beta 3, so these two vectors are orthogonal. Okay. Next thing is, if I do, you can same check for transformation of V2 with transformation of V3. So it will be V2, V3, and you will get beta 1, gamma 1, beta 2, gamma 2, beta 3, gamma 3, 0. Okay. And if you do the transformation of V3 with transformation of V1, so you will get V1, V3. Okay. So that will also be 0. And you will get that alpha 1, gamma 1, alpha 2, gamma 2, and alpha 3, gamma 3 is 0. So you got this. So these all three vectors, alpha, beta, and gamma, are perpendicular to one another. Okay, in case of dot product.
Sir, in
They are
this, you are considering V1, V2, and V3 as orthogonal vectors.
orthonormal.
Oh, sorry, orthonormal.
Orthonormal, I consider. So if I do this, so I got this. So now if I do one thing extra, that if I do transformation of V1's dot product with transformation V1, so it will be equal to V1 dot product with V1. So it is V1's length square, right? So it will be 1. So what is transformation of V1? This vector. So alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. If I do its dot product with alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. So I have to multiply this with this, and this. Okay, I have to do the dot product of this with all these three. So V1 is only going to work with V1 because in these case these are orthogonal already, V1 and V2, so they will become 0. So I will get alpha 1 square V1's length square plus same here. If I multiply this with this, and this, so only this one will work, other will become 0. It will be alpha 2 square and V2 square, then alpha 3 square and V3 square. So it will be 1, it will be 1, it will be 1. And I know that their dot product will be equal to 1. So it will be equal to 1. From here I got alpha 1 square, alpha 2 square, or alpha 3 square 1. So what is this? Means this vector's length is also 1. Same you can verify for this vector, its length is also 1, and same for this, its length is also 1. So I got all these three vectors that are forming, if I represent it as a, what do we say? If I represent it as matrix, so this will be my first column, alpha 1, alpha 2, alpha 3, and beta 1, beta 2, and beta 3, and gamma 1, gamma 2, and gamma 3. So these are orthonormal columns. Orthonormal columns. So now let's do one more thing. If I have a matrix that has orthonormal columns, so if I find out its transpose, so it will have orthonormal rows, right?
Yes.
So this is my first row, second row, and third row. This will be my first column, second column, and third column. And if I do their dot product, if I do their matrix multiplication, so what would that be? This first row's dot product with first column. So C1's dot product with C1, C1 dot C1. Next element will be first row with second column. So C1 dot product C2, C1 dot product C3, and C2 dot product C1, C2 C2, and C2 C3, C3 C3, and here you will have C2 C3, okay, and C3 C1. So this one will be 1 because columns are orthonormal, right? This one will be 1 and this one will be 1, and rest will be 0, 0, 0, 0, 0, 0. Okay. So
Sir,
here you got what?
sir, can you just go down once, please?
Okay.
So in this one, sir, the one which you have taken, TV1 equal to W1 is alpha 1 V1 plus, sorry,
Alpha 2 V2.
alpha 2 V2 plus alpha. So this is a transformation of V1?
Yeah, this is W1. This is the transformation, and I wrote it as because I want to represent it as matrix format, right?
Okay.
So that's why I have to write it as some linear combination of this V1, V2, and V3. I'm using same basis for domain and codomain.
Understood. Okay, okay, okay.
Then I found this, and this. So now I got this. So what I got, R transpose with R is identity matrix. Okay. So I can also say that from here that R is equal to, R transpose is nothing but R's inverse as well. Right? So I can say that R transpose is equal to I is equal to R transpose R. Okay, so if these two conditions are satisfying, and here, sorry, we don't have to go that much. So what we got, column vectors are orthonormal. And if this condition is also holding, this one, so their row vectors are also orthonormal.
Sir, but that is true only for the transpose, no?
Sorry, what? This
Uh,
one.
yeah, row
I said,
vectors.
yeah, R transpose R is equal to identity.
Sir,
Okay.
when you say the row vector are of A is orthonormal, basically it's speaking about the A transpose. No, it should be row vector of A transpose are orthonormal.
Listen, listen. What I am saying here, I got this where this is my matrix R. Okay. I got R transpose R is equal to identity, right?
Yes, sir.
So this transpose has row vectors as orthonormal, and this has column vectors as
Yes,
orthonormal.
orthonormal. Yes, sir.
Okay. Now I am saying that how can I write this I? I can say that it will be if I multiply both side by R inverse.
Hmm.
Okay. So what I will get here, R transpose is equal to R inverse.
Yes.
Okay. So if I write down one thing that um, R R inverse is equal to I. Is that correct?
Yes.
I can write transpose in place of inverse.
Yes.
R transpose is equal to inverse. Okay, sorry, identity. Now,
So
if you look here,
when you do this, so basically the problem is the statement is saying that row vector of A is orthonormal, but when
yeah,
you derive this R into R transpose is equal to I is
it
same as
says
R
that
transpose into R equal to I. So it really doesn't change that thing, na sir.
no, it is not going to change anything because
So that statement is saying it is for A vector, sorry, A matrix. Shouldn't it be for A transpose matrix? That's what my question is. I
okay,
got your entire derivation. I agree with that.
okay, so
But my doubt is still that should it not be related only to A transpose?
okay, I am going to
That
tell
is
you
the
one
thing.
more thing. Okay, just once, just some time. Give me. Uh, you got these two conditions, right? You are aware of this thing. That first thing is R transpose R is identity,
Yes,
and
sir.
next you got R transpose is identity. These two
Correct.
conditions. Okay. So if you look a statement just above it here, rows of a matrix are orthonormal if and only if this is possible.
Okay, so
And
if
column,
this satisfies, then both columns and rows are
is-
orthonormal.
yeah, if this
Okay.
condition satisfies, then columns, and if this satisfies, then orthonormal. Is that clear now?
Yes, yes, yes.
Sir, can you please show the statement again?
Okay. Here, here.
Okay, so the rows are orthonormal only if A into A transpose is I, right?
Right. Okay.
Okay, and basically rows are not orthonormal in this case, right? A transpose into A.
Yeah, in this one, no, it is not. Sorry, if it is possible, then rows are, and if it is, then columns are.
If both satisfy,
So
then
both
both are.
satisfied, both are right.
Yeah.
Okay, because in general, for whatever we are finding, you are finding that A into A transpose is equal to A transpose into A. So
Yeah, mostly we deal with this. Yeah.
in this case, both the rows and normals are orthonormal, right?
Yeah, right. Okay. So let's move. Which of the following matrix is orthogonal? We have to find out. Okay. Orthogonal means if I multiply it by its transpose, then it should give me an identity matrix. So if I multiply this with its transpose, that is nothing but it is same matrix. So what would that be? 1 here and minus, no, 0 here. 0, 0 here and 1 here. So you can see that I'm getting identity matrix in this case. Next one, if I multiply, so I have to multiply 1 by root 2, 1 minus 1, 1, 1. So 1 by root 2, 1 by root 2 will be 1 by 2. And inside I will have 1 times 1 minus 1. Sorry, I have to do the
negative.
I have to do the transpose. So 1 times 1 and minus 1 minus 1, so it will be plus 1. Okay, so
2.
1 times 1 minus 1, 0. 1 times 1 minus 1, 0. 1 times 1, 1 times 1, 2. So it is nothing but identity matrix. Okay. You can check for this, and I'm going to do this only. Okay.
Sir, we can check A transpose into A also, right?
Yeah, you can also check that. Okay. Or you can check both if you want to. So if I multiply this with 1, 0, 1, 0, 1 and root 2, 0, 0, minus 1. So if I multiply this, so what I will get 1 times 1, 2, so 1 by root 2 I also have to multiply. So it will be equal to 1 by 2 times this matrix. 1 times 1, 1 times 1, 2. 1 times 0, 0 times root 2, 1 times 0, it will be 0. 1 times 1, 0 times 0, 1 times minus 1, 0. 0 times 1, 0. Root 2 times 0, 0 times 1, 0. 0 times 0, root 2 times root 2, it will be 2. And 0 times 0, 0. 0 times 1, 0. Root 2 times 0, 0. 0 times minus 1, 0. 1 times 1, 1. 0 times 0, 0. Minus 1 times 1, minus 1. So it will be 0. 1 times 0, 0 times root 2, 0, minus 1 times 0, it will be 0. 1 times 1, 1, 0 times 0, 0, minus 1 times minus 1, it will be 1. So 1 plus 1, 2. So it is identity matrix.
So this option 3 is also?
No, it is wrong.
Okay.
Okay. So up to this part, it is done. Yeah, now whose concept was that? That was remaining? Yeah, and now you can ask your concept related queries, please.
Sir, he had leave.
Okay. Yeah. He left. So that's it. So this is done. So I think anyone else having any other doubt regarding the concepts or any concept that you are facing problem in that, you can ask me now.
Sir, can you please revise that equivalence and that similarity? So I just forgot everything.
Equivalence is nothing. When you can represent this matrix as this form, make sure that Q and P are invertible. Okay, P and Q only. Invertible means determinant 1. Anyone else having any other doubt? Otherwise, I will explain this concept. If anyone else is having other, then you can ask firstly. Your practice assignment related or something like that? No?
So, quick question. So, when we say equivalent means if we can do elementary operations.
Okay, that condition, yeah. It is its characteristics, some of its characteristics that if you can transform A to B using some elementary row or column operations, so then you can say that they are equivalent. And two matrices are equivalent if their ranks matches. Either thing you can apply.
So generally, this is what we learned. Like if we pre-multiply a matrix, that's essentially we are operating in their row space. we are post multiplying, we are basically doing some operation there, column space. So when we go from A to B with the help of P or a Q, right?
Yeah.
So essentially, that's what this is saying, right? If I can go start with the matrix A, do some elementary row operations, then
Yeah.
do some elementary column operations, I can go from A to B through these, then they are
Yeah.
equivalent, right?
Yeah.
That's basically what it is.
Yeah. What it is saying, because elementary row and column operations are allowed. So this is.
And if it is invertible, then I can, it's almost like I'm going from A to B. I can also backtrack. Like I can also
Yeah.
come from B to A to the
Exactly. Yeah.
same. So it's basically bijective kind of situation, right? If I'm,
Yeah. Both directions are possible in that way. Going forward and backward are both.
yeah. Whereas in case of rank, it could be completely different. They just happen to have same dimension, but it's nothing really related. It's almost like a dimension of the space is same, but other than that, there's nothing else.
Yeah, you can say that because rank are going to be same in that case because when we are going from both are of same dimension. So when we are going from one space to another, so the rank should be same in that case. You can say that because elementary row operations we are applying, so the rank will be preserved in that case.
So in real life, if I find a solution, because we do a system of linear equations with Ax equal to B, so if I see A and B are equivalent, so if I solve something with By equal to, let's say, Z, then it's basically, kind of gives us the equivalent answer, right? That's the whole practical application. I can transform a problem in Ax, B to something else. I can still get a solution, equivalent solution, maybe
Yeah,
computationally
you
easy.
can
And
like that. Yeah, you can means you can transform the this A matrix, and then you can apply some. You can get means you can change its columns. Sorry, rows. If you are applying rows, or the same way we did a row echelon form solution. If you are aware, then we reduced it using elementary row operations. So it is changed from that part, but here we are changing it the same way we are changing here. Exactly.
Sir, if let's say I'm having a 3 cross 3 matrix,
Yeah.
and the rank is of 3,
Yeah.
and similarly I'm having B as the 3 cross 3 matrix, rank is B. So even though the components of these two matrices are different, we can say that they are equivalent.
Yeah, they are equivalent in that case.
It means that I can form B from A. This is what we are trying
Simple.
to say.
You can think that if A you are having and your rank is 3, so
Mhm.
if you reduce it to reduced row echelon form, so it will be
Okay.
an identity matrix, right?
Yes, yes, yes. Both will have same RREF, sir.
Yeah. From
Yes,
identity matrix, you can form this B.
yes, yes, yes. Got it.
Okay. Anyone else? I think that's enough for today.
सर वो सिमिलर वाला भी एक बार
Okay, similar one. Okay, I will explain that. Let me stop the recording first. Okay. Where is this list? This lecture is about to be kicked, so let it stop here.